And the first, microphone.
Oh, sorry.
Okay. Does it work? Okay. Thank you very much. And first of all, I'd like to thank organizers for giving me this opportunity. And it is my great pleasure to present our recent study about spontaneous motion and the deformation of a droplet by chemical reaction. The motivation of my study is from a biological phenomenon, which is cell motility. Of course, cell motility is a very, very complex phenomena, but recently some studies indicate that there is some correlation between the motion and the shape of the moving cell. So here, for instance, this is moving amoeba type cell, and they measured some correlation between shape and the motion, and claim that there is some positive correlation between that. And another movie is that here this is the keratocite cell, and actually this is not complete cell, but the fragment of cell. But still, if you and the circular shape, this cell doesn't move in the circular shape. But if you change the shape a little bit like this, then this fragment of cell starts to move in a certain direction. And the other one, this is nothing to do with cell biological systems. This is just alcohol droplet on the water, and this is very simple experiment, but still you could see some deformation and the motion, some continuous motion. This is due to the alcohol. This alcohol droplet is evaporating on the water, and coupling with the motion and the deformation, then it's continuously moving like this. So the key important issues in these phenomena, I think, is that these phenomena is force-free, and also the system break the symmetry, rotational symmetry, and it chooses one direction for the motion. As for force-free, we have already had a high-level discussion in this morning, and therefore I don't need to add many things. But since I will be concentrating on the continuum description, but focusing on the different interesting aspects. So therefore, I hope everybody agrees. And I just wanted to add here that this force-free type force-free motion is not very special. This is quite well known in the classical phenomena like diffusiophoresis, which is a particle moving in the concentration gradient, and also thermophoresis, which is the particle moving in the temperature gradient. And this is also true for the Malangani effect, which is the motion driven by surface tension gradient. And here's some schematic picture of the system. So we have some droplet or bubble in the surrounding fluid, and suppose here's a higher temperature and here's lower temperature. And the surface tension is typically lower here and higher here, which creates some tangential force acting along the interface between this droplet and the surrounding flow. And this force creates flow outside and inside the droplet. So inside is this kind of flow, and outside is kind of flow indicated by blue arrows. And eventually this droplet moves in this direction. So, and the force-free, which means that the stress tensor times normal vector integrated over the surface, over the interface, goes to 0. This is the actual condition determining the velocity of the droplet, which is described like this. So velocity is proportional to the temperature gradient and the proportional constant of surface tension to the temperature and the viscosity inside and outside the droplet. So this is the motion under external external gradient. So no mechanical force, but still the motion under some external gradient. So here is the example. Also, we have seen in many presentations about the Janus particle. So this Janus particle moves in a certain direction under the uniform field. So here is the example of Janus. The silica bead is half coated by gold, and under the uniform and isotropic laser, and this gold part is heated up, and it starts to move. And actually, the temperature distribution around the particle is something like this. This is indeed asymmetric. You know, here this part is higher temperature, this part is lower temperature, and this creates some kind of motion of this particle. Since this particle has asymmetry, this has some polarity. Therefore, it has some rotation and diffusion, and therefore the actual motion is something like this. It looks like a Brownian motion, but the diffusion constant, effective diffusion constant, is much enhanced by the self-propulsion. So so far we have discussed about the motion and the imposed asymmetry in the system, but we are interested in some spontaneous asymmetry breaking, and I would like to show you two examples of experiments. One is oil droplet. So this oil droplet is moving in the water, like this, and possibly interacting with each other. So what is special in this experiment is that they use some special surfactant, and the surfactant is schematically described like the head part and the tail part, and this surfactant first dissolve in water and come to the interface, and then at some characteristic time scale it decomposes into the two parts, like the head part and the tail part, meaning that this surfactant loses its function as a surfactant. And so therefore this system is non-equilibrium in the sense that there is a continuous flux from outside and inside, and then it moves. I will see more detail later. And the second example is that the droplet coupled with some chemical reaction. So this is water droplet in oil, floating on the oil, and this droplet contains some chemical reaction, which is called the Belousov-Jabotinsky reaction. And following this wave appears inside the droplet moves forward and backward. And believe me that there's net displacement of the motion the net displacement is very small, but they exist. This second example looks more complicated than the first one because there's a wave inside the droplet, and also motion is not steady. It looks oscillating and so on and so on. But it turns out the second example is much easier than the first one because here is the model of nonlinear chemical reaction for the Belousov-Jabotinsky reaction, which is called the oligonator model. So these are basically two variable nonlinear reaction diffusion equation, and the U and V corresponds to some chemical state corresponding to the color in the previous movie. And we assume the surface tension is proportional to the B, and actually this is measured in the experiment. And we couple this equation with the hydrodynamics Stokes equation because the velocity of the droplet is slow. And then we have some effect of flow in the reaction diffusion equation, but it turns out this effect is very small. So therefore, this phenomena is essentially dominated by the pattern inside the droplet. And we just solve the nonlinear reaction diffusion equation numerically, and also at the given surface tension distribution, we could solve the Stokes equation and analytically. Therefore, we could get this kind of motion, and there's other patterns for the nonlinear chemical reactions, which is like a spiral wave, and also scrolling wave, axis-symmetric wave, like this. And also in experiment, we could measure, this is a bit hard to see, but there's spiral wave inside the droplet, and following this wave, this droplet is actually moving. So, okay, and so let's come back to the first example of the experiment. I told you this is much more difficult because there's no the symmetry breaking is really driven by the motion itself. So we really need to think about the coupling between the motion and some concentration distribution. And also we are also interested in deformation. And recently, these kind of equation of motion for the velocity of the droplet and the shape of the droplet described by second-rank tensor was proposed in the group of Takaota, and based on the symmetry argument, because so there is coupling term, but due to the symmetry, this is the possible lowest order coupling between velocity and the shape. And they also derived this equation from the reaction diffusion, nonlinear reaction diffusion equation. But my question is that is there some mechanical structure inside these kind of equations? And also in the phenomenological theory, we couldn't say anything about the coefficients, and we don't know what kind of structure in this equation. And the consequence of these equations, the coupling between motion and the deformation, is that the motion is not only straight motion, it's just straight translational motion, but also some helical motion like this, and some kind of rotational motions. This is what they measured for the single deformable particle, solving the equation that we have seen here. And also they extended the analysis for the collective behavior, and Andreas Menzel, sitting somewhere here in this room, also analyzing this kind of thing. So, okay, so the model we are discussing in this talk is something like this. So this is basically diffusion equation with some damping term, and this is the source term. Source means that there is some production of chemical from the inside. This is described by this blue, and some chemicals, coming from the droplet, which creates some gradient like this. And this the term is characterized by amplitude of A, and theta is step function. So which is, and Rg is the position of the droplet. And actually, there are two contributions from hydrodynamics in this equation. One is here, because the motion is determined by some mechanical structure, hydrodynamic equations somehow. And also here's a convective term, which is really concentration is convected by flow. And in this talk, I will neglect this term, but we could include this term perturbatively in our result, and we found that actually this term does not change the result qualitatively, meaning that what we get, we get some kind of amplitude equation for this kind of system, but the structure of the equation do not change by including this kind of term. So we expand this equation close to the critical point of the phase transition between the stationary state and the moving state, which means that the velocity at the critical point at the velocity is 0. And like this, using the Green's function, this is described in the Fourier space, but the Fourier space of the concentration field, and the Green's function of this linear operator, and the diffusion constant. And this expansion is essentially expansion in terms of velocity, or R dot, or Pecquet number if you want. And since we are interested in deformation of the droplet, it is a bit hard to solve this kind of problem with the boundary body problem. We rather use some continuous description for the droplet, using phi is 1 inside the droplet and phi is 0 outside the droplet, and continuously connecting this function like this, and taking sharp interface limit. This is something. This is kind of phase speed description of the system. So then we couple this nonlinear concentration distribution with hydrodynamics, and here is a standard Stokes equation because close to the critical point the velocity is small. But there is another contribution. There's force, and this pi, which is sometimes called Korteweg stress, arising from the surface tension of the system, and this B is roughly speaking a surface tension of this droplet, and we assume this surface tension is proportional to some concentration field C. And since this in the sharp interface limit, this grad phi is essentially a normal vector, so therefore this means that this stress is something like surface tension times Ni and J. And what is good for this kind of description is that when you take the sharp interface limit, we can convert this kind of problem into the boundary value problem, which is standard Stokes equation with velocity continuity and the stress jump. And the stress jump is arising from the surface tension, which is surface tension is because surface tension is force acting on the at the interface between droplet and the surrounding flow, which creates some jump in the stress. And indeed, if you apply under given linear concentration field, we could solve this kind of problem exactly, and then we come up with exactly the same solution that we could get by solving this conventional boundary value problem for the Monagny effect. So here is the force acting at the boundary, and we have the force has two components. The one is Laplace pressure, which is proportional to curvature and the surface tension. The other one is tangential force, which is proportional to the surface gradient of surface tension. And we could expand surface tension in terms of spherical harmonics in 3 dimensions, and the cosine sine in 2 dimensions, and then we could analyze the structure of force moments in this system. So we expand this the velocity field in terms of moments of force. This is just multiple expansion, and the T is also in tensor of Stokes equation. So this is a derivative and the second derivative, and so on and so on. And the monopole, which is just integral of force, should be 0, and is 0, and as it should be. And also and by the way, this monopole is corresponding to the velocity field, which is proportional to 1 over r. And dipole is expressed like this. And if you choose a proper axis, then the dipole is given like this matrix. And but the important thing is that this is proportional to gamma 2, the second. So L2, the second mode of the spherical harmonics, and this is proportional to 1 over r squared. And this corresponds to this is associated with the deformation of the droplet. And the next order is quadrupole, which is expressed like this. And the interesting thing is that this the quadrupole contribution leads to, of course, gamma 3, the third mode contribution, but also the contribution like 1 over r cubed times gamma 1. And this is related to the velocity of the droplet. So therefore, the droplet, the moving droplet driven by Malangoni effect is actually the origin is the quadrupole in this kind of force-free system, because there's no monopole in the system. And the similar kind of stuff things were pointed out by Frank Uricher and Jacques Paul for the phonetic motion. But here is the same story applies for the Malangoni effect. And I would like to call negative gamma 2 as a puller, positive gamma 2 pusher, because once we know that at the given distribution of surface tensions, when gamma 2 is higher here and here, which is positive gamma 2, and the lower here and here, then it creates some force, tangential force described by red arrows, which creates a flow like this, which actually pushing fluid. And since surface tension is higher here and lower here and here, therefore it deforms like this, because the curvature should be smaller for this for higher surface tension. And in the opposite case, when gamma 2 is negative, then everything is opposite. The force is like this. Tangential force is something like this, which creates a flow. It's actually pulling, and then the shape is something elongated along the direction of the motion. And since we assume the surface tension is proportional to the concentration field, so and together with the dynamical equation for the concentration field, we have some closed set of equations. And the argument of pusher and puller, we have already seen in many presentations, so how important they are. So therefore, I don't need to add many things, but I just want to say that pusher, the sign of gamma 2 is very important, because this determines whether this swimmer is pusher or puller, and actually it determines the collective behavior or macroscopic viscosity and so on and so on. So therefore, we want to analyze the sign of this gamma 2 in our system. So once we know the concentration distribution, we could know the velocity field. This is just Laplace force, Laplace pressure, and times Olsen tensor. And here is tangential force creates also some velocity field. And once we know the velocity field, we know the normal velocity at the interface, here denoted by Vn. And from some geometrical consideration, velocity of the droplet is given like this. And since as we explained, the concentration field is expanded by in terms of velocity of the droplet, this is actually this equation shows some kind of self-consistent equation determines the velocity of the droplet. And we have another kinematic condition. So the normal velocity is equal to some velocity times normal direction, and also the contribution from deformation. And we expand the shape from some reference state, which is a spherical shape with some deviation, so delta R, and the delta R is also expanded in terms of spherical harmonics. And therefore, this equation shows that this is the kind of equation of motion of the amplitude of deformation, so WLM. So in principle, we can get the equation for the WLM and the velocity of the droplet. But instead of doing that, it is better to define the order parameter tensor for characterizing the shape of the droplet by multiplying many normal vector onto the deformation and integrate it over the surface. And we should respect this symmetry so that this tensor should be symmetric and traceless. For instance, we have a kinematic condition in a slightly different way, and multiply some traceless matrix using normal vector, and then we come up with the equation of motion of the second mode, which is Sij. And the same thing, it is possible for the third mode by multiplying just, this is traceless, symmetric traceless tensor for third rank tensor, and we could get equation of motion for the third mode. And so just for intuition, I just want to show you some examples of second mode. The second mode has five independent modes or five independent deformation, two elongation in two directions and three shears, and each of them are described by the set of spherical harmonics like this, the amplitude of spherical harmonics here, and or just a combination of the matrix element of the second rank tensor. This is also true the case for the third rank tensor, which is more complicated, but third rank tensor have 7 independent components, and again these shapes are characterized by the spherical harmonics, like here. And the shape is, roughly speaking, some sort of tetrahedron like shape. And then, so now so here these two equations are essentially what we want to get. So these are amplitude equations for the velocity of the droplet and the shape. And finally we get these kind of equations up to the cubic order in the expansion. So here is equation of motion for the droplet. Here I denote m, but this m is not the mass of the droplet because this system is very small. This is a kind of effective mass obtained by expanding the concentration field. And so there are many parameters, but all the parameters are described by the parameters that we have in the original equations. So we have a linear term, we have a cubic term, so then there's coupling between the velocity of the droplet and the shape, and the second mode is described by this coupling with the first mode, and third mode turns out to be slaved by the first mode and the second mode. So here's some damping term and some effect from first mode, and the coupling with the first mode and the second mode leads to the third mode. They look complicated, but they are just form of symmetric traceless tensor with some appropriate combination of tensors. So the droplets, the translation of motion is the phase transition of stationary state and moving state is kind of easy, because when tau is larger than 1, the linear term becomes positive, and then it means that the stationary state is unstable, therefore it moves in one direction. So I mean, so if you change the parameter tau, and the tau is actually explicitly described by this. So gamma is a proportional constant between of surface tension and concentration. See, here is amplitude of source term, viscosity, density, and the beta is a length scale characterized by the diffusion and the damping term. And by increasing tau, we have some phase transition from stationary state and the moving state. And we could also calculate the velocity of the droplet as a function of the size of the droplet, and we could get this kind of behavior. The mechanism of this translational motion is that since we have, suppose this droplet slightly moves in this direction, so since this droplet creates many chemical, the concentration of chemicals is higher here and lower here, which means that since here we assume the gamma c is positive, then surface tension is here is lower and here is higher, which creates a flow, and it moves further in this direction. This is the mechanism of this instability. And the second mode, as I mentioned, this is the shape of the second mode, and this is the third mode. And the interesting thing is that we are interested in gamma 2. What is gamma 2? And the gamma 2 is associated with the shape of this droplet, and this shape of the droplet is actually determined by the sign of this this term. And it turns out this lambda is always negative. This term is always negative, which means that gamma 2 is always positive, and therefore this droplet is characterized as a pusher. So like this. So some intuitive explanation for this sign is that suppose we have some elongated droplet perpendicular to the direction of motion like this, and there is some kind of contrail of a concentration field, because this guy is moving in this direction. So there's and producing chemical molecules, and so therefore this concentration is higher here. And then, since the curvature is larger here, the concentration becomes lower here at this point, and this point. And then the concentration becomes lower, then surface tension becomes lower, and then its shapes looks like this kind of shape. If the shape is the opposite meaning that the shape is something like this, so then the concentration distribution along the interface is almost same everywhere. Therefore, it never creates kind of deformation. And the another interesting thing is that if we concentrate on the first mode and the second mode, then formally we could write, okay, well, let's concentrate on the first mode. Then formally we could define kind of Lyapunov function or energy function like this, the first term and the second term, which is some kind of harmonic term and some higher order term. And by taking the derivative respect to u, then formally we could get equation of motion like this. So, and this is also the case for the second mode, something like this, if the sign beta times lambda is positive. And as I mentioned, lambda is negative, and we found that this beta is always positive, and therefore, unfortunately, there's no Lyapunov function in this system. So, but well, this is not very, in some sense, this is not very surprising, because we are far from equilibrium. There's no reason to why we have Lyapunov function, but this this is explicitly calculated somehow. And also, we could, since we know some kind of, we know the mechanical structure in the system, and as I mentioned, the stress is described by this kind of form, and therefore we could see what kind of stress acting on this system. And actually, I call this active stress because this is non-equilibrium state and creating some kind of stress, which is not passive stress. And since we don't have force monopole, we have force dipole. The stress from this equation, we could get the active stress, which is something like this. This is kind of the moment of concentration distribution times some prefactors. And we found that this active stress is actually proportional to this term. So I mean, if we translate this velocity as some kind of polar vector, this is nothing but active stress is proportional to pi pj, which is quite standard in the active hydrodynamics thing. And sign here again is proportional to lambda, which means that this is pusher or elongated stress. And if I put some numbers, diffusion constant and size, and some characteristic length, and this is the time scale of Solstam, then we come up with this kind of numbers. Active stress is roughly speaking 100 Pascal. I don't insist these numbers. Of course, it is some numbers are really difficult to measure in experiments, but still, it is. I would say the number is not very, it's not very stupid. So, and then another consequence of the deformation is that the interaction between two droplets becomes somehow strange. So since so suppose we have two droplets, so both create some kind of concentration distribution, and there is overlap which creates kind of interaction between two droplets. And again, we could we extend our dynamical equation for the concentration distribution. Again, we neglect the convective term. Convective term corresponds to some kind of hydrodynamic interaction, but we neglect that. And here is the source sum of each droplet. And again, we expand this size of the droplet in terms of spherical harmonics, and we come up with almost the same equation, but with some additional contribution of from interaction between two droplets. And this interaction is given by, so there is a contribution of isotropic part and anisotropic part like this. And isotropic part is expressed like a kind of potential between two droplets. This term is just proportional to the distance between two centers of mass, and this is some explicit form, but roughly speaking, this is exponentially decays by one exponential beta times the distance between two droplets. So, and therefore, this interaction, isotropic interaction, is kind of Yukawa type potential. And the second contribution is that this droplet interacting differently with the shape like this and this. Well, I think this is quite natural because the concentration field is something like this for this shape, and the concentration distribution is more elongated perpendicular direction to the R12, and therefore interaction should be weaker somehow, and this is described by this kind of things. And interesting thing happens for the next one, another contribution, which is some function of distance between two droplets, and depending on the size, second mode of the droplet times some strange tensors. And this tensor gives the relative position between the droplet. So this tensor is explicitly written like this. R1 to hat is a unit vector connecting between two droplets. And this term means that the interaction of these three situations are same, but these three positions have opposite contribution from this kind of the position. So I think this is interesting because not only isotropic contribution, but also this kind of anisotropic contribution appears from the deformation, which might be not very important for the isotropic and the nematic kind of phase transition, but probably more important for some crystalline-like structure or more anisotropic structure of a collective behavior of the spontaneously moving droplet. So here I just calculate the interaction between the droplet. So therefore, the next question is what kind of hydrodynamics equation could be for this kind of system. So this is ongoing problem. Now we are trying to calculate these kind of things, and also we are interested in fluctuations, and also it might be interesting to include some complex fluid, or for instance, nematic liquid crystal inside the droplets. Then we could have a more closer model for the cell. So finally, I would like to acknowledge these people, and the translation of the drift bifurcation of the droplet was done with these people, and the coupling between the chemical reaction and the translation motion was done with these people. And I would like to thank for your attention.
Is it right that the first two lines you have pure hydrodynamics without any chemistry, or I misunderstood something? What is pure hydrodynamics in your talk without
pure
chemical reaction, or you don't have any?
We have chemical reaction in the sense that
you know results. Yes,
yes, everywhere, because I
see. You don't have results in pure fluid dynamics.
No, because
yeah, understood.
Because here is A, and A appears everywhere in the coefficient of geometry equation.
I misunderstood. Thank you.
So what is the relative strength of the dipole and quadrupole contributions?
Relative strength. I'm not sure I could answer well, but in the case of it's quadrupole concentration. Well, I think it's a bit hard to compare with them because they are completely different in the sense that dipole relates to the deformation and the quadrupole relates to the translation of motion, which is velocity. So they are completely different in a sense.
So I was thinking in terms of the disturbance velocity. So eventually the dipole would dominate the quadrupole.
Disturbance of velocity in a far field, as I mentioned, the far field velocity, not here. So velocity field decays 1 over r square for dipole and 1 over r cube for quadrupole. In that sense, the dominant contribution for the hydrodynamic interaction is dipole.
But the crossover would happen at the ratio of the two coefficients, gamma 2 by gamma 1. So do you have any idea of what those coefficients are?
Yeah, it really depends on how fast this droplet is moving. And if the droplet is moving very fast, then the crossover distance becomes larger and larger. And Yeah, well, I don't have a reasonable answer for that.
I missed where the Yukawa nature of the potential came from.
Sorry.
The Yukawa nature of the potential, where did that come from?
This comes from, okay, this partially comes from dumplings over here.
Where does that come from?
Okay, well, I mean, you could take the k goes to 0 or plus 0, and but this is included in order to somehow generalize the situation.
What's the physical origin of why there's a disappearance of the concentration?
Well, there is many situations. For instance, if you have box, there's some boundary determines the length scale of this k, or if there is some reserve of chemical of chemical molecules, then it also creates some kind of this term. I think there are many situations.
Well, thank you very much. Yeah, and recycling.